Okay, and you asked two questions setting up for this lesson. The first one was, can you think of an approach as to how you would expand the physical network, be it computers, phones, telephone networks, both 4G and others? How would you go about installing new infrastructure to maintain keeping the money in coming in as you go through? The reason is there's basically two approaches, um, both giving surprisingly equivalent answers. One's basically Kruskal's algorithm, which I think of as Krusty the Clown's algorithm. If you know Krusty the Clown, he's a bit random and he's always cheap. Prim's algorithm is a bit more proper and it's always about adding on more. But the point about both algorithms is at every time when you're making a decision, the decision is, am I adding a new node, a new point, a vertex? Am I adding a new node to the network? If I'm not going to create a new node, I'm creating something called a cycle. And there will be another route already to have got there on the graph. And therefore, it doesn't lead to my spanning tree. Now, the purpose of a spanning tree is to say every single point on this graph, all the nodes, can be got to by starting somewhere else. So the route might go, if I'm at F and I want to get to B, may go F, E, B. But the route could just as easily have gone F, D, E, C, B. I can still get across to the network. So it only works if the graph is already connected. That means everybody is connected to the graph in some way. If it breaks, you can't apply either of these because there is no spanning tree. So the purpose of the spanning tree is just to be able to say, what's the smallest network needed for us to connect between different places? So Kruskal's algorithm, and both of them lead to decisions and ideas. But Kruskal's algorithm is look at the next cheapest arc anywhere. Is it adding at least one new node? Does it add another node? Or does it connect up two parts of the graph that are not connected already? So let's just label the point. Let's start with these. So what's my cheapest arc or path? Arc or edge. My cheapest arc or edge is either AD or CE. These decisions do lead to different answers, but they are nearly always equivalent. So let's start with CE, and that will give me a cost of 5. My next cheapest one, AD. So it didn't matter which way round I started, I will have added either of them. Now, if you're doing the exam, they often like you to write down what you've done. So I've just done AD 5, CE 5. Next cheapest one, and look, they're all over the place. It doesn't matter at the moment. Next one is connecting D to F because that's worth 6. D to F for 6. Looking through, what's my next cheapest one? My next cheapest one is one of the two 7s. So I need to choose a 7 to do. I can either do A, B, or BE. I'll connect BE. So creating a point at B, 7. And that's dealt with. Then I've got AB for the other 7. So whilst I'm not connecting a new node now, I'm now connecting two graphs that were separate, and that's fine. Next one to look for is an E. Now, this FE one, the question is it connecting to point? Am I adding a new point? No. Is it creating my graph a new, connecting to bits of the graph which are separate? No. So because both of these are no, We don't do FE. That doesn't appear in my spanning tree at all. But we do BC. Oh no, sorry, we don't do BC either. So BC, B and C are both connected to the graph. They're both on the same network. So the E is not needed. The 8 is not needed. 9, I look at the DB. DB, do I need it? No. So I missed off the AB for 7 and BE for 7. Now you could write down these other ones we're considering and say, no, we're not doing them. But we just want to see which order did we connect these up. So because DB doesn't give me anything new, EG gives me my new node. And that's 9. Now, I know I can stop now. There's a simple technique for this, and this was what the second question was yesterday. I have a total of 7 nodes. On a spanning tree, every node is either connecting to other nodes. Every arc connects to other nodes. And that leads to something called a handshaking theorem. But we have one less arc than there are nodes. And that's how I knew I could stop after 6 arcs. So 6 arcs leads to 7 nodes are connected on a spanning tree. Now this is a minimum spanning tree because we did what's called a hungry algorithm. We kept taking the cheapest ones we could. So my total cost for this is going to be 10, 16, 16, 30, 39. And that's my minimum spanning tree. It is possible sometimes that some of these decisions where I could have done a 7 here, where these 2 7s, where one of them, by doing one of them, I may have actually created a different path. And it's possible to have multiple paths, but we should always get the same minimum spanning tree as long as we followed the rules. So we can wind up with multiple paths. So the Kruskal algorithm, it connects the cheapest places it can. And it goes around trying to find out how to connect them. The other algorithm, PRIMS, is about adding to an existing network. So if we were trying to build our telephone network, Kruskal's algorithm would have said just keep adding cheapest connections together and get as many people connected as quickly as we can, or as many places connected as quickly as we can to something, so we're getting the money coming in somewhere. PRIMS says let's take the most expensive place, or a place, and let's consider where can we get to next to grow the network as if it was coming out by an algorithm. If we started as if it was being grown naturally. So PRIM's algorithm is actually quite natural. He's not the first person who actually came up with it. There was a guy called Yannick who discovered it about 30 years earlier. But it was back in the time when some papers didn't go between Czechoslovakia and America particularly well. Strangely enough, this was also discovered afterwards, about 2 years after PRIM, by the same person who did the distance graph, Dijkstra. So it's not often referred to as a Dijkstra algorithm, but some people refer to this algorithm as being the DJP. Dijkstra, Yannick, PRIM. And it allows us to create graphs. Now it starts with a known place. So I'm going to start at point G. So starting at G, and I say, right, which path can I add to it cheapest now? Well, the first cheapest one is E. Now, there is a nice thing with Dijkstra's, with PRIMs, that, a bit like Dijkstra's algorithm, you're always looking to add new nodes to move forward. So I look at G, G connects to E, I then look at E and G and say, right, what are the cheapest arcs I've got coming away now? So I've now got both of these, they're both connected. I'm now looking to grow the network a bit further. Obviously the next one is to go up to C. So C for 5. So starting at G, we did G and E for 9. Then we did E to C for 5. Keep growing the network. So what's the next cheapest one? The next cheapest one is BE for 7. So EB for 7. And I'm up to this one. Grow the graph again. I can go AB for 7. Or BA for 7. Keep growing it on. So now I'm coming round to go A to D for 5. And finally, last one to connect to, trying to get to F, the cheapest way to get to F is D. So D goes to F with a 6. Now, because there were no options in this graph as we go through, we didn't have to make a choice and flip backwards and forwards between, do I want to add this one or that one? The graph we have is the same. It doesn't always give exactly the same graph, but it will always give you the same weighting. So I'm going to give you another graph in a moment on here. And the question is, how many different spanning trees are there? And try using a mixture of methods, both Prim or DJP and Kruskal. Again, I knew I'd stopped here because I've now connected the last node. So here's a new network for you, 5 towns in Cleveland. And the question is, can you find how many paths there are? How many minimum spanning trees there are? This one has multiple, and we'll discuss it at the start of the next video.